Hello, everybody. My name is Joe Andresen, graphics engineer for JavaFX, and this is Jim, 2D graphics architect. And we're going to talk about the new Canvas feature in JavaFX 2.2, how it's different from Scene Graph, and the goodies inside. Some legal stuff. So what we're going to talk about, we're going to put some context around Canvas and talk about the Scene Graph rendering API very briefly, and then go into an overview of the Canvas rendering API, kind of the ins and outs of what we did, and then go into some example applications, problems you may run into, solutions. And then if we have enough time, we can go through a ton of demos and answer questions. And another thing too is that this talk is going to shift from talking about API to talking about strategies when you would want to use Canvas, when you'd want to use the Scene Graph. Not necessarily saying Canvas is better than the Scene Graph. It's just there are some cases where maybe Canvas might be more useful or easier to use than the Scene Graph. Okay. So very briefly, many of you, if you know JavaFX, has a Scene Graphs model of rendering, which is basically just a graph of node objects. Nodes are traversed, and then those results are rendered to a destination, which can be, now in 2.2 we have render to image, so it could be an image, it can be a scene, so the destination can vary. Nodes, you have rectangles, circles, ellipses, controls, various kinds of nodes, and a node provides different features with the Scene Graph, animation, layout, effects, properties that you can animate and things. And the Canvas rendering API, Canvas is rendered as an image, and Canvas itself is a node, but when you render to a canvas, you're using method calls, and it's kind of an immediate mode style kind of API. So in the Scene Graph, where you're creating a rectangle object and then adding it to the scene, to the root of the scene, for Canvas, you're creating a canvas, adding it to the root of the scene, and then saying, getting a graphics context from it and saying, you know, g.draw rect or g.fill rect or what have you. So one of the big points about Canvas is it's persistent. So when you write pixels or render to the canvas, it is going to stay. Those pixels are going to stay there until you clear them. And lastly, as you'll see, some of the API from JavaFX, blend modes, effects, and colors, paints. Those are applied to the Canvas API as well. So Jim's going to...
Okay, so I'm going to briefly go over the API for Canvas, show you how it compares point by point to what we've done with Scene Graph nodes previously. So the basic API is, as Joe said, you have this canvas object in a new package, JavaFX Scene Canvas, which is a node, and you use that to hook yourself into the Scene Graph. It provides a method to get a graphics context, and there's one of those graphics contexts per canvas for the life of the canvas. So if you keep calling that, you'll get the same context back with the same state in it. So you have some persistence of, you can call that and get a rendering context from anywhere, and it'll be set up as you previously set it up. The context has a bunch of setters and getters for various rendering attributes. It has methods to render actual graphical objects. It has a graphic state stack so that you can save and restore your state to do temporary changes that only affect a few calls and then return to the context you came from. And it has a current path instead of a path object, which is more of a PostScript style of rendering than a Java 2D style of rendering or a path node style of rendering. So what kind of attributes do we provide? Basically, they're almost all one-for-one, similar to an attribute you would find on a shape node. But there are some differences in how they're interpreted. So for instance, it has a set fill and a set stroke, which sets the paint for filling and stroking. In the node, in the shape node, if you set a null, it means don't fill or don't stroke this object. On a canvas, you can't set a null because the paint is just always there available for when you call fill something or draw something. There needs to be a paint because you're calling fill something. So we don't allow the nulls. Set fill rule to change the fill rule from even odd to non-zero. In a shape node, if you say set fill rule of null, we just ignore what you did. In the canvas, if you set a null, we just pick a default non-zero. So it basically becomes a way to say even odd instead of non-zero, but we just applied an interpretation to null similar to, and I think we didn't mention this yet, but we kind of modeled this loosely after what they were doing with the HTML5 so that HTML5 programmers would be familiar with what we're doing. And in HTML5, if you set an unknown value, it interprets it as non-zero. So we're kind of doing that here. You can set an effect on a node, which will apply that effect after the node is rendered. And you can set it on a canvas, which will apply after every single rendering operation. And in both cases, if you set it to null, it means there's no effect that's going to happen. You can set a blend mode, which controls how your pixels blend into the stuff behind what you're rendering. And on a node, if you don't set one on a node, it means use the blend mode that was set by one of your parents. In Canvas, we ignore the null because you always have to have a blend mode. There's nothing to inherit from. It's an immediate mode API. All of the stroke attributes on one of the main differences is on the shape node. It's a full node with a huge number of properties and a number of different namespaces. So saying something like set width doesn't make sense when it's got a lot of things that have width on it. So it tends to have all of the method names be set stroke attribute, set stroke this other attribute. Whereas on Canvas, it's just a rendering API, so the names are a little bit simpler. So you'll see set stroke line cap, which is very verbose on the node because it has a rich namespace it has to compete with, and just set line cap on the canvas. For example, width, the shape node will allow you to set it to anything, but it will clamp it to be a positive number. Canvas has specific rules that we adopted from HTML5 about ignore 0, any negative number, or any infinity, and just don't change the value. And similarly, shape will default if you set a null for the line cap and the line join, whereas we simply ignore them on Canvas because that was more in line with what HTML5 did. The miter limit was just clamps to a useful value on the node, and we ignore the standard values from HTML5. The clip attribute is fundamentally different. Shape, being a node, has an arbitrary clip that you can set, which can be any node, and it uses the visual representation of that clip node to mask what this node renders, which is very flexible and very, you can do a wide variety of things. You can even set a group to have a whole bunch of objects that contribute to what is clipped against this node, whereas Canvas has a more basic typical graphics interpretation of a clip, which is just there are a bunch of paths, and you can add a path, or you can't add a path to a clip. You can clip to a new path, which intersects the old clip with the new path, so it's constantly getting smaller as you clip to more paths. The font and text attributes all use the same objects that the text node used, but the names are slightly different because of the change in namespace, and also what we do in some default cases is different. There is a default font that the nodes will use. If you set it to null, we ignore it as per what HTML5 did. There were a couple bugs I ran into when coming up with this slide. The null for text alignment, it looks like it's supposed to be ignored, but there's actually a bug in that they try to dereference it, they get a null pointer exception, and it's at a part of the scene graph, which basically it's bad, don't cross the streams. So you can look up those bugs and hopefully they'll be fixed soon, but it's not bad in that your machine will die, but your scene graph won't be happy after it. But in most of those cases, I believe that what it looked like it was intending to do was to ignore the value. Basically setting an alpha is like a fade on an operation. So on a node, we call it opacity, and the whole node fades as the alpha goes to 0. For rendering, it's an additional opacity on top of the paint's opacity on every rendering operation. And in HTML5 parlance, they call it global alpha instead of opacity. Finally, transforms. Nodes tend to have objects you can set. They have a few helper methods. You can set a scale on your X using a single method or a single property, but then they have a generic observable list of transform objects for setting everything else, whereas in Canvas it has a current transform matrix and you modify that with additional methods in a more standard practice. The rendering primitives are pretty much the same. Almost all of them are. On the node shape side, you have a node that is that shape. On the canvas side, you have a fill and stroke method that fill and stroke it. The notable differences are that a round rectangle and a rectangle are the same thing in the nodes. You just set an arc width or not, depending on whether you want the rounded corners. In Canvas, it's separate methods. The polyline node allows you to set a fill, so you can fill a polyline, even though that's really what a polygon is for, but it still lets you fill it. There is no fill polyline method on the canvas because you should be using fill polygon if you're going to do that. And finally, on the paths, there's obviously a node for the scene graph, and in Canvas, rather than having one fill path method that takes a path object as an argument, it has a current path that you build in the graphics context using methods, and then once you've built it there, you call the method fill with no parameters, and that means fill that current shape, or stroke it, or use it as a clip path. Finally, for image rendering, they both use the image object, but you embed that in an image view for a scene graph, whereas you just call a draw image method for Canvas. Path elements are mostly the same, just the names have been changed. There's a list on a path node that you can clear. On a canvas, you call begin path to clear out the existing path. And slight name changes on some of them. We tended to follow the HTML5 naming conventions. And the only difference in behavior is that the arc node and the arc primitive on Canvas actually do different math. The Canvas, which is based upon HTML5, follows the PostScript arc operator in the way, and I'll show you an example of what it does, whereas the arc node follows a different set of math that allows you to specify with different points and different radii and how those are interpreted to construct an arc. Finally, there is no way to just add a rectangle to a path node's path list, whereas Canvas provides a convenience operator called rect, which takes 4 parameters and adds those as path segments to the current path. And both of them can take an SVG path specification. So this is the different arc they have in Canvas and HTML5, and it follows what PostScript does. You basically have the current point, you give it 2 more points, and it draws sort of a corner going to the first point, through the first point to the second point, and at the corner it inserts an arc of the appropriate radius. And you notice from the middle example, if the radius is large enough, that arc can actually be inserted behind you, opposite of what you were expecting. We have a demo we'll show later because we have to switch machines. It's just not worth it for right now, but I'll show it to you later. And, okay, the state stack. It's very PostScript-like. It has a save and restore, which is like PostScript's gsave, grestore. It saves and restores almost the entire state that you would think, except for some reason the current path was not part of the graphic state in HTML5, and we adopted that. The current path is part of the state in PostScript, which is kind of one place where they kind of broke with the PostScript rendering convention, and we followed that instead of doing the PostScript. And unlike PostScript, which I think has a constant referring to how many times you can save and restore, we just allow you to save until we run out of memory, so hopefully you won't save 1 billion times and run over your 12 gig of memory on your desktop. And the state and the graphic state stack are the same every time you call get graphics context 2D. That doesn't reset anything. The object is in the same state as it was the last time you used it. So we preserved all the state and the whole stack of, you can save, go away, and a new method could start up, use it and restore, and you'll restore to the state that was saved over in the previous event handler. So it's probably bad programming practice. I'm not saying to do that. I'm just describing the behavior of the object. Miscellaneous. You can, if you came to the image ops talk yesterday, we talked to you about all the things you can do with a pixel writer, which is basically set pixels and set rectangles of pixels from a buffer. And you can get one of those objects from a graphics context and use it to push your own pixels. There's an apply effect method which does something that isn't really available anywhere in the scene graph, which takes the whole canvas with everything rendered into it up to the current point and applies an effect to all of that. It would be kind of applying an effect to a whole scene, except it just does it, and then the results are back in the canvas, and you can do it again. So you could apply, you know, a blur over and over, and it would get really, really blurry over time as you applied it over and over, because each one is applied to the results of the next that go back into the canvas. It also does have a set effect, but that effect is applied only on a given rendering operation, actually on all rendering operations, but individually. So if you set it and then you say fill rect, we will apply the effect to that fill rect and then put that in the scene. And if you follow that up with fill oval, the effect is still set. We'll apply it to that fill oval and put the results of that affected oval into the scene. And then finally, the clip intersects the current path with the current clip, similar to the way PostScript works. There is no set clip or reset clip. You have to use gsave, the save and restore commands if you want to apply a temporary clip and then back it out, because there is no way to reset that. And back to Joe.
All right, so now we're going to kind of shift themes here and go into like strategy. You have the scene graph, you have Canvas rendering APIs. When would you want to use one over the other, and so on. So pros and cons of the scene graph. Obviously, you have picking, you have the timeline and properties that you can animate, and you know, for interactive components, buttons and such in your UI, it's pretty easy in the scene graph, obviously, to implement that stuff. And the big con of the scene graph is kind of the idea of primitives via objects. So you have to define lots of objects to get the rendering you're looking for, where if you're doing a simple rendering, it can maybe be a little more verbose than you want. With Canvas, you know, you can render a shape with one line of code. And the canvas itself is a node, so all those properties and picking and stuff you can pick on the canvas. You still have some of that benefit. And of course, the major con of Canvas is, well, all you're doing is rendering. You don't get any of the fancy stuff, which, I'm putting that as a con because it kind of contradicts with the scene graph in this sense, but there may be a use case that you have where all you need is rendering. Yeah. So I'm going to go over an example application, the ensemble path preloader. So way back, probably about a year ago, before Canvas existed, we were actually recording the screencasts that are on the JavaFX website, and we thought, man, wouldn't it be cool if we could, have a preloader for JavaFX that isn't just a boring animating circle. Like, what if it was actually a cool looking preloader? And then we thought, well, that's kind of difficult because it's just a preloader. It can't do anything complex. And soon enough, this is what we came up with. But the scene graph version, we render a path node, and then we use two groups of moving rectangle nodes, and then we add a blend to that group. And then we have an array of path transitions that is connected each to a node, and we use that to traverse or to animate the rectangle nodes along the path. So we're going to show you that one.
Okay, which one? The first one?
Graph version. So I'm basically going to show you the scene graph implementation and the Canvas implementation. So you want to go ahead and run it, and then
okay. So can we turn the microphones on the table on? Are they on? Hello? Okay. So this we're first going to run it to show you exactly what a preloader is. It's basically visual eye candy that can be running while you're basically loading stuff in the background. So this loads quickly, draws something to keep them entertained. Meanwhile, in the background, you're loading huge amount of media or the rest of your application or whatever. And this one is basically chasing around that word with some highlights. So to get that, basically, there's an SVG path defining the shape of the ensemble word, and that's rendered once to provide sort of the etched racetrack that those highlights are going to run through. And then two groups are constructed with a bunch of rectangles in them that will move around following the shape of that path with, first of all, a highlight color that they're filled with, and then an effect that adds a glow of the same color to them. So each group has its own drop shadow of a similar color added to it, and then a whole bunch of rectangles are added into those groups and assigned to path transitions so they follow that SVG path along. And again, you have to have a path transition per rectangle, so there's two arrays of path transitions that are being used. And the end result is you see the dark gray stroke with the black fill of the base rendering of the word, and then the two groups of cyan and magenta rectangles that are being animated along it and then blurred with a drop shadow to create a glow effect. Okay.
Right. And just for context, how many? Let's go to the top for the number of rectangles.
So that included
Right up a little. Right there.
2,000 rectangles per highlight.
Per highlight is 2,000.
So 2,000 cyan rectangles and 2,000 magenta rectangles chasing around.
Right. And okay, so that's the scene graph version.
Show the canvas.
We have a canvas version that if we run.
So I'll run it first just so you can see it does essentially the same thing.
Yeah, exact same thing using Canvas.
And in this case, it creates, so in the previous example, we had two groups that had effects on them. So we had a bunch of cyan rectangles in one group with an effect on the group, and a bunch of magenta rectangles in another group with an effect on that. And with a canvas, you can apply effect to a canvas, or you can set an effect that will affect each operation you do. So the choice is between set one of those glow effects and render the 2,000 rectangles, which will mean that that effect will be individually applied 2,000 times, which gets tedious and slow, or somehow collect that group of rectangles together somehow so you can apply the effect to it. And the only way to collect them for applying the effect to those groups is by using separate canvases. So this actually uses these three canvases. The root has that X racetrack rendered into it, and then the other two have either all of the cyan rectangles or all of the magenta rectangles in them. And then every frame, it simply runs through and renders all of the rectangles into the appropriate groups, and at the end applies the appropriate effect to the appropriate canvas to get the glow on that canvas. And so here you have the black canvas in the background, the magenta canvas with the magenta rectangles and the magenta effect, and the cyan canvas with the cyan rectangles and the cyan effect, and they're rendered on top of each other because a canvas is transparent by default.
Right. So between the two, couple of things I want to point out. The actual animation, the thing that's driving the animation, between the canvas and the scene graph, it's actually more or less the same. We have a timeline which is connected to a property, which is just going between 0 and 1. It does it the same in the scene graph, and it does it the same in Canvas. Obviously, the first example uses many nodes, where this example uses many method calls. And then it also uses the multiple canvases instead of the group.
You don't need an array of path transitions?
Right. So for this for the Canvas version, rather than using an array of path transitions, I just had a dummy node that was the front of the line, so to speak, and then the rest of the draw recs just kind of filled behind that. So yeah.
Okay.
I guess we could switch back.
Okay.
Yeah. Uh-oh.
Freaked out here.
My slides aren't coming back. Let me... My slides aren't coming back. Let's see.
Detect? It's not detecting.
Yeah, it's not detecting the slides. I don't know. I think it was that unplugged for too long.
Could be just the wrong resolution.
Oh, yeah. Okay. Thank you. Okay. Crisis averted.
Is there a way to hook both of these on?
So we went over the Canvas implementation and the scene graph implementation, comparison summary. Right, so the many nodes versus one node, animation's more or less the same, and the properties are set on the nodes as opposed to being global attributes that you save and restore on the canvas. So another example that I wanted to, our concept really, is layered rendering. Like Jim said, canvases are at default transparent. And so, with layered rendering, you group commands, rendering commands, or rendering operations into separate images and then blend them together. Image composition, it's a big part of Photoshop and a lot of image tools. In Canvas, this is a really important thing. It can have visual implications using apply effect, obviously, but also it has performance implications because with the canvas being persistent, it kind of acts like a cache. So you can, in our example we showed you, that racetrack was only rendered once. In the scene graph, that's kind of automatic, but in Canvas, you have to really pay attention and make sure that you're not going to render your path every time that you do that do frame. So the setup code would render it into the canvas once, and then we would render on the other canvases kind of over it. So what does layered rendering get you? It gets you, like we were saying, static versus dynamic content rendering. You can use apply effect to apply effect to a subset of your rendering operations, and then it's really similar to a group node, but obviously a lot more lightweight. So.
Did you want to show demo?
Yeah, so we're going to show.
We should probably switch once to the demo machine.
Okay.
So go through their slides, and then we'll switch.
Okay. So we have from here on out, we're going to show various maybe problems you might have with Canvas and strategies that we use for updating or problems with the scene graph, for example. So common problem number 1: scrolling and updating. I think. Do you want to talk to this?
Yeah. Yes.
Yeah.
So in the scene graph, you've obviously constructed a whole bunch of nodes that are representing what you want to render. And if you want to make a change to them, such as to scroll, then that can invalidate all sorts of information we've cached about those nodes. Or you just want to change the layout of one part of it. And so there's a tremendous amount of work that has gone into optimizing how the changes of bounds propagate to parent groups and to sibling groups and affect the layout. But still, in some cases, you have a very simple layout, and it's obvious what this change will do to everything else. And that can be communicated by code that you wrote with your pre-knowledge of how things are set up. That does it with just a few lines of code, whereas we have to go and compare bounds against each other across a huge group of things that didn't move, but we don't know until we've done the calculations. So basically, there are cases where you have a very simple concept of laying out, but it's not something that can easily be conveyed through the way you've grouped your nodes in the scene graph. Obviously, we've done a lot of work on that goes pretty fast, but there's sometimes scalability problems. It might work great for a couple hundred nodes, but if you've got 10,000 nodes, then suddenly those calculations start adding up. And also, it's just work that can be completely eliminated by a piece of code that knows what it's doing. So Canvas allows you to just basically do what you know needs to be done, but then obviously using that, you give up all of the flexibility and capabilities you get with nodes to basically just add event handlers onto a given node without having to do your own picking code. So it depends on the ratio of how complicated your layout is to what you need to do with it. If you don't need to do a lot with it and it's a very simple layout, you might actually be able to render it faster than you could express it in nodes. And then a question we got was, Canvas is not implicitly out of the box set up to participate in layout managers. But if you want to have a canvas in your laid out control, how do you get it to play with that? And so Joe wrote an example that shows exactly what you need to override to make it work with layout managers. And we're gonna wait until the end of the slides to switch to the demo machine because we've had problems with the switching. We only want to switch once. And we're ready for the...
One thing to note also about layout with a canvas is that since there's two ways of kind of resizing your canvas, maybe you would like to just scale the content that you're rendering, or maybe you would like to expand the viewport so that you can include more content. Layout is up to the guy using the canvas. And so that's kind of why we decided to make it extendable.
So one thing we didn't show about the path preloader that shows off the layered rendering was that he actually had created this other timeline which would animate all three of those canvases against each other to make it more obvious what was going on, but we had that commented out for the first demonstration purposes. But if I start playing that timeline, then you'll see the three actually can be moved around independently because it's three separate canvases with the lowest layer, that's the little racetrack, and then the cyan and magenta layers. That was just to point out that it is being done with three independent canvases. Finally, there we go. Where do we want to go?
Scrolling?
Scrolling, so contact list. Yeah. One thing I did when we were first experimenting with scene graphs was I did the standard contact list like you might have on your phone, which you have 1,000 contacts and it needs to be scroll back and forth. At the time, our first iteration of the scene graph, pre-JavaFX, actually spent a huge amount of time calculating all of the bounds of everything when all you did was move it by 10 pixels. We've gotten way better than that in JavaFX, but still that's work that doesn't necessarily need to be done for a contact list where it's just now we're at a different, the contact list can see these contacts, that's all it needs to be written. So I wrote Joe wrote a little demo and I worked on it that basically just creates 1,000 contacts, or we actually up to 2,000 contacts. And then basically animates scrolling up and down through those contact lists and prints out how fast it can do it. And we call this make scene method so that we have two different implementations, one that will use a scene graph to make it and one that will use a canvas. So the scene graph version creates a scrollable pane, creates a group containing a background rectangle, first name, last name, phone, sets those into a group with translations on each one, and then returns that pane. And it sets a property that's what you need to animate to get it to scroll. In this case, we just grabbed the vertical value property from the scroll pane. And you run that, and here it goes. So that you can see we've got the gradient background fill, and we're each contact is 3 names, and we're getting about 17 frames per second, scrolling that back and forth in a scroll pane. Then created a canvas version, which is similar, but it doesn't have a lot of capabilities. Like, I don't have a scroll bar on this. If I didn't have that animation driving it, I'd have to write a whole bunch of code to add a scroll bar to set the property to get it to scroll, which I didn't have to do because I just did an animation that scrolls it back and forth. So it's deceptively the same amount of code, but there's a lot missing here that the other one buys you for free. However, you run it, and it's getting 400 frames per second. Basically because the contact list has no real intelligence at all at how it's laid out. It's just a big long list, and you can use a simple division to figure out which contact is supposed to be drawn, and you only draw the 5 contacts that are drawn. You need no bounds calculations, no update everybody's transform pass. But again, that's an example of the huge ratio of such a simple layout to not needing many capabilities, because I didn't need a scroll bar. I had an animation to scroll me. But it shows you the difference in performance when you can get rid of all of that. So again, choose how much flexibility you want versus whether you can do it yourself, and those are the trade-offs. Another example of updating is, we keep calling this Christmas tree, but really it came from I think like the stock market traders have multiple monitors with a huge number of little cells that are telling them what's happening with the different stocks, and they'll blink red or green depending on whether the stock's going up and they want to buy it. And there's just a huge number of them laid out in a simple grid to get huge visibility across a variety of stocks. And that's a stress test for a lot of things. There was a version of this that ran in Swing for them to do performance work in Swing. We have a version that runs in Scene Graph to do performance work in Scene Graph. I created the simple version of it just for demonstration purposes. So there's a base, the base class that just defines how many cells we're going to have, and then it asks the subclass to make all the cells and then to update them with a new state. And the 3 states are green, white, or red for low, normal, or high. And then it just has an animation timer to deal with updating 100 cells for each frame and then printing out the frames per second. So we have a version that uses Scene Graph to make a cell. It just makes a little group containing a rectangle and a text. And then to update it, it just changes the fill color and changes the text in the node. And when you run this, it gets lots of blinkies, and it's running at 90 frames per second. I have the VSync turned off for these, so it can go above 60 frames per second. So it gets almost 100 frames per second, lots of blinky things. And the canvas version, to make a cell, it really just makes a canvas once. So it checks if GC is null, it makes the canvas, and then the next time it gets called to make a cell, it doesn't really make it. It just draws it using the update cell. When it's told to update to a new state, it just simply draws that cell again. And you end up with 170 to 180 frames per second, so roughly double the performance. Again, an extreme ratio of how simple the layout is here and how easy it is to go and just update the pixels that need to be updated using prior knowledge about what the application's doing, compared to that's about all you can do is go draw that rectangle. There's no, picking support would have to be manually coded. You get it for free in the Scene Graph. So that's another example of layouts and scrolling.
The
Layout.
Okay.
Oh,
The layout.
so the example of how to get your canvas to participate in layout. There's this layout test. It's a very simple application. I'll just draw it first. All it is a giant rectangle with this alternating white-black pattern. But as I resize the window, you see it's actually being controlled by the layout manager of the container it got put in. And so it's responding to where it needs to go.
And so really, I listed kind of the steps in the layout slide, but I just extended canvas. So
here's,
yeah,
where is it?
it's a separate file.
Oh, separate file, sorry.
Canvas layout.
So canvas layout extends canvas. You override the is resizable to say, yes, I am. You override the preferred height and width to return your own height and width. And when you're called to resize, that's abstract.
Yeah. And so
back in the demo, he overrides that, and when it's called to resize, he changes the size and then calls his doFrame method to re-render the code.
right. And so what I was saying earlier, how you resize your canvas matters. You may want to scale your content or whatever, and so that's why I provided this method, so that you can kind of do whatever your canvas needs to do to resize.
So basically, resize is the only method that needs to be custom per canvas that wants to be laid out. But the rest of them are common to any canvas that wants to participate in layout. Next. Go to
Cool
questions.
demos, maybe.
One thing I wanted to point out, the apply effect enables you to do something that couldn't be done. I don't know if you've been to some of my talks in previous Java 1s. I have this little eye candy that I wrote in Swing using buffered image, and I just push pixels around in pretty patterns. And you can't do it with a scene graph because each frame is a modification of the frame before it. It's not its own definition. And so finally with Canvas and the ability to apply effect on a canvas and get the results back into the canvas, you can create Zoomy. Yay! So Zoomies just basically inject some color into the scene and apply some kind of smushy displacement effect to get pretty pictures out of it. And in just a second, I'll go to one of the more startling ones. Hello, there. Woohoo. So, eye candy, the best reason to create canvas. I think at this point, let's switch to questions.
Yep.
Are there any 3D canvas? I mean, you can do 3D with no sync, right?
Right, so the question is there any 3D capabilities in Canvas? And at this point, no. We followed the HTML5 example. They're all 2D, and in fact, their method is get context, and then the string you hand in is 2D, which gets this. So we called our method get graphics context 2D with the intention that if we want to then provide a 3D rendering canvas, we could then have a different method which returned you a 3D oriented rendering context. But for now, all we have is that get graphics context 2D, and we only support 2D operations.
Any roadmap, like can you share your secret?
There isn't anything to share. So that can be something we can discuss on the mailing list and see if people want to get an effort started. But they're working on 3D now, 3D major heavyweight 3D nodes. Right now we have the ability to add a couple of Z transform properties on a node that can get you some 3D, and they can actually do a lot of cool things with it. But if you went to the talk yesterday, or was it Monday, they actually showed you like the ability to create meshes and have cameras fly through them. So that's just getting started on the scene graph side. Canvas is going to wait to see how that plays out, and then before we even make a roadmap.
Makes much more sense in 3D because, you know, if you do charts, I mean, it's fine to do 3 nodes, there's not that many items. But if you do 3D charts, you get square the number of items. And that's where the difference between canvas versus the graph version should be broken out.
Okay, so the comment was for charts, if you try to do 3D charts, you can greatly increase your node count if you're doing it with a scene graph, but with Canvas, you could do it much simpler.
Yeah.
And you know, I've seen plenty of demos in Java 2D where they just did the 3D calculations themselves and rendered paths. Yeah, so you have that capability as well.
But that doesn't use the acceleration of it because you can, like another question, how much is actually accelerated in the graphics?
I didn't get that.
What's
So,
how much of the stuff is accelerated?
so the thing you have to be careful is the canvas is kind of an immediate mode style. You're not you're once the commands are drawn, it's done. But any work you have to do is going to have to be executed. I mean, I want to say simultaneously. It's not really simultaneous, but there's not a ton of stuff cached on the graphics card. In the scene graph, we do use that as a kind of a strategy, and that's what I was saying in one of the slides where you have to kind of knowingly treat Canvas like a cache. But when you talk about 3D, it very much is a good idea to want to cache stuff on the GPU. And so if you're using an immediate mode style API to render 3D stuff, it kind of gets a little hairy. So you need to make sure that the strategy that you're using the canvas for is the same kind of strategy that the canvas is catered to for rendering.
That's a good point because most 3D APIs are scene graph based in the first place.
Getting back to 2D, how much of that is using acceleration?
All of it.
Yeah, we hardware accelerate everything you see happening there. Yeah, just as we do the similar nodes on scene graph. It uses the same rendering library. Yeah, that's actually part of the reason why we don't have, get pixel reader from a canvas is because the pixels haven't been created in hardware yet until we do a sync up, and it would just be a nightmare, and it would be slow reading them back off the card. So we don't want to encourage reading from your canvas until we know how to get that responsibly done, because everything is done in hardware. Any more questions? Or another question? Or more questions about 3D? I don't know.
Want to show more demos?
What?
Mandelbrot.
So when we were testing the canvas, we found a lot of HTML5 demos, and we started porting those over. Some of them don't run well here because like they come up, they don't have the screen real estate on this projector, and I didn't test them at this real estate, and they come up with a window that just doesn't do anything. Here's a fluid solver that I think I did run earlier that Joe found on the net and ported. That I don't know if you want to. Yeah.
So it basically uses a canvas and then draws small rectangles and then runs a fluid simulation on them.
So the smoky stuff is basically like ink in a fluid that's being distributed by the momentum that you pushed through the fluid with.
And the JavaFX version, so there's a version exactly like this in JavaScript, we get double the performance. So with a fluid solver, that's a huge deal because you can have more iterations, you can have a bigger image to do it on. So it actually made a pretty big difference.
There was also this Mandelbrot. I haven't tested to see if this comes up. Oh, it works. So this, running on JavaScript, even with the best browsers, this lets you zoom in on the Mandelbrot set, and then it'll draw the next frame. And usually it's measured in how many seconds it takes to draw the next frame, whereas we're instantaneous because it's all Java code that gets compiled by Hotspot. And so you can zoom in as far as you want, and voila.
256 by 256. Yeah. Yeah.
On the transformations, so like say zooming or magnification. So I've got a product on a different technology stack. But one of the things we do is sort of create an app and then zoom in and zoom out. And yet there's some objects we always want to draw one pixel thick lines no matter what the zoom level is.
Well,
Do that with
there's a couple of ways. Oh, because you want the locations to modify, but not. We don't provide a separate transform for coordinates versus attributes. So your paints will be affected by the transform, and your line width will be affected by your transform, and the decorations of the line are affected by the transform. For doing something where your maps are zooming, though, it might be just as easy to for the amount of transforms you're doing, just do it yourself and figure out what the new locations are. It's 4 multiplies and 2 adds to get a nice 2D transform going for your locations, and then you're rendering with just the fixed line width of whatever you want.
Actually, there's 2 more things I want to bring up in this presentation that didn't quite get to make it in the slides. Was a guy who did a blog post about new 2.2 JavaFX features, render to image pattern, and canvas. And what he was able to do was render kind of a custom canvas look kind of pattern image, and then he used render to image to save it to an image, and then used image pattern to put it as a background to one of his controls.
I actually showed something like that in my image ops talk, and I have one basically that uses a render to image to. I don't have anything that uses canvas. Sorry. But basically just creates dynamic images on the fly to use as an image pattern. I could have done this with canvas as well, but I did it with nodes and render to image.
So that's one thing. And then another thing, I was talking to Kirill, who we work with, who worked on the 3D stuff. When he saw Canvas, his first impression was, can I use Canvas to render a bump map? And in the future, that will absolutely be doable. Yeah.
How much do you guys actually enable with JavaScript Canvas? I mean, could you just run existing JavaScript code to Mesh or JavaScript engine and just run it in JavaFX?
So you have to port it, but one of the exercises we did modeling after the HTML5 canvas, the reason we did all of these ports was to see how what it's like, because we want somebody who's an HTML5 developer to easily go from one to the other. And it wasn't. It's pretty straight, one-to-one, pretty much. It's very easy. Oh yeah, that's something.
Is this Canvas?
Yeah.
Yeah, this is something that Jasper did for animations for one of the demos he's writing, and he's basically doing this on a canvas. All of those have custom locations every screen, so you don't get any advantage out of all of the work we do to run through to calculate the bounds on everything and the transforms. You render them, and that's all you need done with it. You can forget everything else about it. So that's an advantage of Canvas, is low footprint for doing something like this. Any more questions? Okay, that's it.